Hello everyone, I am Francesco Laccone and I'm going to present you a recent development in the field of bending active structures, entitled FlexMaps 2.0. Bending active structures are structural systems that are based on the use of curved beam or shell elements which are initially straight or planar and are then elastically bent to obtain a 3D formactive shape. The work I'm going to present builds on computer graphic research that aimed to realize small-scale objects out of flat patches, like this one. This approach is called FlexMaps and discretizes the surface of a generic object, like this you see in the slide, into submodules, so mesostructures, with a spiral shape. So these spirals are optimized that once they are actively bent and assembled, the final shape results as close as possible to the target shape. The idea behind this work is to use the spiral to define and control locally the material behavior. And there are at least two advantages of using a spiral. The first one is that having a spiral path instead of a linear path means that we need less bending energy to achieve the same curvature. And second, the spiral is very easy to handle because we can modify the stiffness only changing the geometrical parameters. So it is possible to obtain custom mechanical properties without changing the material, and so to accommodate locally the curvature demands. At the equilibrium, the stress redistributes uniformly among the panels that have different stiffness. And this is important because if instead we use all equal spirals, we will end up like a kind of balloon surface. This approach has been recently validated at the architectural scale with this project entitled FlexMumsPavillion we realized for the IASS 2019 exhibition in Barcelona last October. And with this result in mind, we developed an automatic and integrated design methodology to use FlexMaps at the architectural scale, and we tested it in a demonstrator project that you are seeing in the slide that was realized at the School of Architecture of the University of Technology of Sydney. And we selected a very complex shape and we worked in a constrained time and space. The whole structure is made of 15 millimeters thick plywood that has been CNC machine milled. And in the next slide, I will show you the main steps of this methodology and how these were practically applied to the demonstrator. Just to fix our ideas, this is the construction system. So basically the panels are flat at the beginning in their rest position and they are bent by hand. So the object reaches its final shape under appropriate boundary conditions once all patches are individually bent and tied together. We developed a connection between the patches that guarantees full strength, and we use this connector we named key connector that has an interlocking shape, and thanks to the friction and to this shape effect, the connector developed a sufficient resistance in preparation for a couple of through-hole M5 bolts that definitely lock the two extremities in their position and avoid any relative movement. They work as a kind of key. Concerning the shape, there are no special restrictions. In particular, there is no need for the shape to be funicular or no need to be developable. Any shape is feasible as long as it is at least stable in the equivalent continuum. So the shape has been selected among a set of possible candidates, and the red framed is the shape we selected for our demonstrator. The surface needs needs then to be discretized in quads. And to drive the quadrangulation, we computed a smooth cross-field that follows the main curvature direction of the surface and aligns with the border. This step produces a boundary aligned as regular as possible quad mesh with few singularities. The average size for the edges is selected to be about 26 centimeters, because this is a manageable size for both the fabrication and the assembly phase. In the optimization phase, every patch is populated with the spiral, and in particular, each quad embeds one single spiral. This is the reason why we need a quad mesh. The spiral is simulated with a reduced model having average properties, and in the optimization, the spiral is tuned to result in a certain stiffness, so that the structure will be as close as possible to the target shape. The patch layout is selected to minimize the distortion from flat to bend position and to facilitate the assembly of the structure. While the size S is given through the quadrangulation, the size of the spiral, the optimizer can work on the twist and on the thickness, the other two parameters. And various spirals can be obtained from the most flexible top left to the most stiff bottom right in this spirals matrix. But for aesthetic reason and to avoid local weakening, in this case we force the algorithm to stay within a restricted design space, which is of a constant width of 15 millimeters and a twist range between 40 and 180 degrees. So in the end, each spiral has a variable arm length, but a constant cross-section of 15 by 15 millimeters. An important step we added is the FEM validation. Indeed, the optimization is stiffness-based and provides no control over the material stress and just a limited control on the deformation. So we used a solid finite element analysis to calculate the exact deformation and to verify that the stress is results within the material capacity. And finally, we used this model to estimate the overall safety level. The model is automatically produced in ANSYS and consists of two phases. In the first one, each patch is individually analyzed and bed up to the candidate bend position. And in the second step, the connectors are bonded together, and the dead load and any other load is applied. We are able to automatically generate the files for the CNC milling machine, and we had the chance to use this big scale machine at the advanced fabrication lab of the UTS with a bed size of 3 meters times 1.5 meter, so that the fabrication at the end took about 1 week, only 1 week. There are some aspects that cannot be automated, but deserve careful attention. One of these is the floor. The floor is not merely aesthetic, but has also to provide resistance to the thrust force of the structure. And this is why we designed an interlocking floor with this Penrose pattern that is made of only two types of tiles. Additionally, the floor has also to resist to bending, and this is why we embed a couple of ballast iron weights within each edge beam. We fabricated the structure in about 3 days, manually bending one patch at a time and connecting to the neighbors. I would like to point out another important detail, that is the arch beam we used for the free boundary of the surface. These are made of a couple of lamellas and have two main functions. The first one is to preserve a correct distance between the connector of the boundary. And the second one, very important, is to guide the patches to preserve their deformed shape during the assembly. So to conclude this project, demonstrate how FlexMaps can be efficiently integrated into a real-scale architectural design process, and it can be adapted to a very complex design. With this method, the whole process from the conceptual design to the assembly structure took about 1 month, but we have to consider that there are some design steps that were not automated. In the end, the structure is both time and cost effective, and it is also very efficient from the structural point of view. Thank you all for your attention.